Hello students, in the previous video I explained the training algorithm of Madaline. In this video I'll explain the training algorithm of Madaline. So before going to the training algorithm part, let me give you a brief introduction to Madaline. So Madaline stands for Multiple Adaptive Linear Neuron, and it consists of many Madalines in parallel, and there is a single output unit known as Madaline layer. So the architecture of Madaline is just like a multilayer perceptron, where Madaline acts as a hidden unit between input and the Madaline layer. Here, in case of Madaline, the weights and bias between the input and the Madaline units are adjustable, whereas the weights and bias between Madaline layer and the Madaline layer are fixed, and normally it is said to be 1. Just like Madaline, here also the training can be done with the help of delta rule. So now the training algorithm. So just like Madaline, we initialize the training by initializing the value of 3 parameters: weights, bias, and learning weight. And for simplification, we set the value of weight and bias to be 0 and learning weight to be 1. So the training process continues. The step 3 to 8 will continue until a stopping condition is met. Then from step 4 and 6 will be continued for every bipolar training pair. S is to T, where S stands for score and T stands for target. That means for each input there will be a target or a label, which is the desired output. So first, in step 4, we activate each input as SI. That means we give a score value to each input. Here I goes from 1 to n. That means there can be n number of inputs. Then we obtain the net input at each hidden layer. That means Madaline units, using this equation. I guess you guys are already familiar with this equation. We can calculate the net input to a neuron or a Madaline unit by calculating the summation of weighted inputs and the bias. Here I goes from 1 to n because there can be n number of inputs, and j goes from 1 to m. That means there can be m number of Madaline's units in the hidden layer. Next, we apply an activation function to obtain the final output at the Madaline and the Madaline layer. And we already know that here a bipolar activation function is used. That means output can be reached from 1 to -1. So the equation of the output at the hidden Madaline unit can be represented using this equation, and the equation for output at the Madaline layer can be expressed in the form of this: y equal to activation function of y in j, where this y input is the calculated net input of each of the Madaline units connected to the Madaline. See, we already know that there are multiple Madaline units in the hidden layer, and there is only a single Madaline unit in the output layer. That means this m number of Madaline units are associated or connected to this Madaline unit with the associated weight. So here Qj represents the number of Madaline units in the hidden layer, where j can be 1 to m. That means m number of units, and vj are just associated weight between each of this Madaline and the Madaline, and here B0 is fixed and it's 1. So after calculating the output, the most important part is to calculate the error and adjust the weights. Now, if you remember, the Adelines are just like perceptron, and it uses a bipolar activation function. That means it's mostly used for linearly separable data. So signum activation function is a bipolar function, and its output value is 1 when the net input is greater than 0. Output is -1 when net input is less than 0. It is 0 when it's equal to 0, and the curve of signum function goes like this. So here, when your net input will be positive, you already know the net input is calculated as a summation of input into weight plus the bias. So when all the net inputs are positive, then it gives a positive output. When it's negative, it gives negative output. When it's equal, it just gives 0. So just notice it carefully. In case 1, suppose our calculated output and the target output is not same and the target value is 1. So if your target value is 1, that means your calculated value is -1. So just assume that in this Adeline units, there is a Adeline unit QZ where the output's supposed to be close to 0 because your target is 1. So for this particular Adeline unit, the values are mismatching. Your target is 1, but your calculated output y is equal to -1. So if you consider for this particular QJ Adeline, the value is negative or close to 0, that means you are going to adjust the weights and bias only at this QJ Adeline unit. So just like the Adeline, the updated weight will be the old weight plus alpha, the learning weight, into the error into input. Here just check the error. Here error is the target minus your calculated output, that means t minus u. Here t equal to 1, so here it's 1 minus y. The y is your qi and j, which I already covered in a previous slide. So the error term is the target minus your calculated output. So similarly, bias will be updated as old bias plus learning weight alpha plus the error term. Okay. So next, let's just consider the case 2 where y and t are not equal and t equal to -1. So in this case, just consider that in this hidden layer, there is a Adeline unit where the net input value is positive. So your target is -1 and you are getting calculated output y equal to 1. That means for this particular UK Adeline unit, your net input value is positive, whereas it's supposed to be negative because your target is -1. Remember, in signum function, when all inputs are negative, then you get a negative output. When all the net input is positive, then you get a positive output. So since, just consider for this particular Adeline unit, your value is positive. Therefore, the weight and bias updation will happen only in this QK Adeline unit. So similarly, weight and bias updation equation is like this, where new weight will be old weight plus alpha learning weight into the error into input. Here t equal to -1, so here the term is -1 minus your output. That means output that you get for this particular K Adeline unit. Similarly, the bias associated with this particular K Adeline will be updated using this equation. Okay, now the third case is when your Y and T are same. So in this case, there is no need to change your weight and bias because your calculated output is just same as your target output. That means your network has accurately predicted the target output. So, and last, this test for stopping condition, which will happen when there is no change in weight or the highest weight change occur during the training is smaller than the specified tolerance. So, in case of Madaline, we have three cases when target output is not equal to calculated output.
Here's what I found.
And when target is equal to calculated output. So in case when target and computed output is same, there will be no change in weight and bias. When target and calculated output is different, that you have to consider when your target is +1 and when your target is -1. If your target is -1 and you are getting +1, that means you have to adjust the weights at those Adeline units where the net input is positive. That means you have to convert or adjust all those weights and bias associated with those particular Adeline units where inputs are positive, and you have to make it a negative in order to get the targeted negative output value. Then if your yn that means targeted and computed value is not same and your target is 1, that means you are getting computed value as 1. That means you have to adjust the Adeline units where your net input is close to 0. That means it's not positive value. So in order to match the target value of +1, you have to adjust all those Adeline units where the net inputs are -1. So I hope it's clear for you. If you have any doubts, you can ask again. Thank you.